Hello everybody, my name is Surya Venkatesan. Welcome to my data mining topic presentation. The journal article I chose is slightly older, from 2016, but it's the only journal article that fit the criteria that we were given and also the topic of my interest, depression. So here is Fusing Data Mining, Machine Learning, and Traditional Statistics to Detect Biomarkers Associated with Depression. The authors are listed, and I am obviously the presenter. Well, let's get right into it. Let's go ahead with the introduction and significance. In order to fully understand the journal, we should at least take a glance at the background. The background is depression. 350 million people are affected by depression, as per statistics by the World Health Organization. Unfortunately, this number is only projected to increase as the population grows bigger, social isolation post pandemic becomes a norm, and economic and fertility decline in first world nations. Unfortunately, many cases of depression result in suicide, which is why it is a serious issue we must address since the outcomes are dire. This paper tries to look at biomarkers as predictors for depression. Biomarkers are measurable biological values that are used to detect illnesses. An example you might be familiar with is blood sugar or A1C levels to detect/predict diabetes. Finding valid biomarkers that can predict depression allow for proper treatment and earlier intervention. Someone who is at risk of depression could be treated before they develop it. This is significant and the best application of this journal. After all, prevention is the best cure. Looking at the dataset next, it is important to understand our dataset and why it was chosen so that we can have full confidence in the analytics that this journal does. This data is from 2009 to 2010 from a survey done by the CDC, the National Health and Nutrition Exam Survey. This survey is conducted yearly, but not everything in the survey is measured annually. This year range is one of the year ranges that yielded the depression results that met the parameters for the study. This year's set, even till today, is the last big and public depression data set by the CDC for the NHANES study. It's a comprehensive data set. It includes the lab results we need for the biomarkers, as well as the PHQ-9 questionnaires. The PHQ-9 questionnaires are part of the survey called Patient Health Questionnaire. Consists of 9 binary questions asked to patients. It's commonly used as a depression diagnostic tool across all clinical settings and relies on patient input and honesty, which may be biases and setbacks for it, but honestly, there are no better options when it comes to dealing with something like depression, unfortunately. It is not super large, but it's a larger data set compared to the alternatives. As you can see, there's 250 biomarkers and 5,000 plus participants. It's also a representative data set. It's nationally representative of the American sample, so all across the country from all types of people from all walks of life. So the people who conducted this study also lacked the funding to do their own survey or to get their own data. So this was the next best option. And the public nature of this data set did help. And at the time of the study, the depression data set from this, actually even the PHQ-9, was an unused data set, even though it was 6 years after the survey was conducted. So these are the reasons why this data set was chosen and a little bit about this data set. Here's a brief overview of the methodology. If you remember the title of this paper, it is Fusing Data Mining, Machine Learning, and Traditional Statistics to Detect Biomarkers Associated with Depression. Let's look at the first part of this journal title, Fusing Data Mining, Machine Learning, and Traditional Statistics. That's a hint to how this methodology setup works. Step 1 is the data mining, as we pine through the data to do missing value imputations. Step 2 is the actual machine learning. Step 3 is the traditional statistics to derive proper conclusions and results. Let's look at this each step at a time. Let's take a look at step 1, multiple imputations. Unfortunately, a common problem in large datasets is that they're littered with noise and especially missing values. The NHANES dataset is no exception to this. In order to make things more efficient, any biomarkers which have over 70% missing data were excluded from analysis. Remember how I mentioned that the dataset had 250 plus biomarkers before? Well, after this, it only had 67 biomarkers. This was a large but needed loss, as it would have led to a lot of assumptions and inaccuracies if large swaths of data had to be imputed. Next is looking at the missing value themselves. Do we deal with more missing completely at random, MCAR, or missing at random, MAR values? MAR, as we learned, can be imputed on. This data had a prevalence of MAR values over MCAR, so imputations are needed. MICE imputation was used. MICE stands for multiple imputations using chained equations. This imputation method predicts MAR values by using other variables and data. In the context of this journal, age, race, self reported health, and journal were the quote unquote other variables used to predict our missing values. The data was stratified by gender, meaning men and women were imputed separately. This was done due to the differences in the biological biomarker makeup by gender. 20 different data sets were imputed. Since the imputed values are predictions, 20 data sets were used so that the results could be pooled. This allows for more accurate data and analysis. Now, steps 2 and 3, which I'll discuss next, just keep in mind that they were run 20 times on each imputed data set. The key takeaway of step 1 is that we now have 20 different mice imputed data sets with 67 different biomarkers. Step 2, boosted regression. This step is the bulk of the machine learning part of this journal. It uses multiple additive regression trees, also known as MART, a subset of boosted regression trees. This methodology starts off with a weak prediction. From this weak prediction, we add trees based on residual errors. Each new tree should shrink the gap between the predicted and actual values, thus improving the model. In the context of this journal, we are looking at inputs of PHQ-9 factors and biomarkers, and the outputs would be the PHQ-9 scores. The output score would then be binarized to a yes or no for if the patient has depression or not. The method of measuring used in this journal is feature importance scores. Each variable is given feature importance scores based on three things. One, how often it is in the regression trees. If a variable is in the trees a lot, it is probably useful. Two, how early it is in the regression trees. If it is super early in the trees, it probably means that it is a prime decision making variable and is responsible for an important split in observations. And the third one, how much error it reduces. This one is self explanatory. As stated earlier, each new tree should shrink residuals, so it shows how accurate the variable is in terms of being a predictor for depression. Important scores were averaged across all 20 models. A 60-40 split was used for validation in order to prevent overfitting. Overfitting is when instead of predictive analytics, the machine learning algorithm memorizes this particular dataset and relies on memory patterns rather than informed predictions. Training/validation splits are done to prevent this. Big takeaway of step 2 is that 21 biomarkers are selected based on the criteria displayed on the right, and based on MART analysis aggregated from all 20 imputed models. The selection criteria is this one that I'm talking about right here. All right, let's go to step 3, the final step. Step 3, logistic regression. A 50-50 training validation split is used here to prevent overfitting. Usually, validation splits are 80-20, but our dataset is smaller to begin with. So that's why we use 50-50. Logistic regression is done on the 21 biomarkers chosen in the previous step. Logistic regression is the right type of statistical analysis here since the outcome would be binary. Yes or no for depression based on PHQ-9 score. Outputs for this step are the pseudo R square for model fit, area under the curve for prediction performance, and odds ratio for the directional effect of each predictor. The purpose of this step is to translate machine learning results into statistically significant results for interpretation. The key takeaway here is that we have statistically analyzed and interpreted our aggregated data from all 20 imputed datasets and selected key predictors based on p-value adherence. Looking at the results, the three predictors we have here are the only statistically significant variables among the 21 biomarkers from step 2. We have red blood cell distribution with an odds ratio greater than 1, meaning a positive correlation with depression. Serum glucose with an odd ratio greater than 1, once again meaning a positive correlation with depression. A total bilirubin odds ratio way under 1, meaning a negative correlation with depression. It acts as a protective factor. However, there was significant interaction between bilirubin and the Mexican American Hispanic and smoker groups. These had stronger associations, meaning total bilirubin is less likely to act as a protective factor for these groups in particular. So, coming to the conclusions and reflections, what they have discovered here is possible evidence of biomarkers of depression. As stated in the beginning, this is good because these biomarkers could be used for early intervention for patients that could possibly develop depression. If I were to continue the research that these amazing researchers have done, I would like to repeat it with a bigger and newer data set in a hypothetically perfect world where I had access to that. I love the study, but the glaring cons of the dataset being older and smaller are a bit difficult to ignore, though I understand the extenuating circumstances of the researchers. With this dataset, however, I would like to test the linkage of these biomarkers with other mental illnesses and see if I can map possible predictive co-occurrences. With that, my presentation is over and I just want to thank you all for watching. Here are the informational references, the slide imagery citations. Thank you for watching.